Hey everyone, today we're going to finish up chapter 3 and we're going to discuss electrons and chemical properties. Last time we talked about the energy of electrons and how we can determine where electrons exist in an atom. And it is very confusing, so I did post a worksheet that allows you to fill in orbital diagrams and determine the electron configurations of atoms and elements. So hopefully that helps. And today we're going to talk more about, again, chemical properties. Now, first we have to talk about what's called a valence shell. So the valence shell of an atom is the shell that contains electrons with the highest N value. So remember, we discussed how there are different energy levels or different shells that electrons can exist in. So if you have an atom with, let's say, electrons all the way up to energy level 4, all of the electrons in energy level 4 are considered to be in the valence shell of that atom. And those electrons we call valence electrons. So those are the highest energy electrons. And these are the electrons that really determine the chemical properties of elements. So atoms that have the same number of electrons in the valence shell have similar chemical properties. So down below we have magnesium, calcium, and strontium. And all three of these elements are in group 2A, also known as group 2. And let's write out the abbreviated or noble gas configurations for each of these three elements. So for magnesium, we previously said that the noble gas that comes right before magnesium is neon. So we can put neon in brackets. And then there are two more electrons that magnesium has, which are located in the 3s orbital. So its noble gas configuration is neon 3s2. And then calcium, its noble gas, or the noble gas that comes right before it, is argon. And calcium has two more electrons than argon, and they are located in the 4s orbital. And then strontium is right after krypton, and it has two more electrons than krypton, and they are in a 5s orbital. So if you're not quite sure how I got these electron configurations, please go back to the previous lecture and just make sure that you understand how I got these configurations. If you are confused, please talk to me. You can schedule an office hour through Calendly, and that link is on the main page of the Canvas website, or you can also always email me too. Now, you might have noticed that there are some similarities here with these electron configurations. So you'll notice that each atom or element has two electrons in an s orbital. So that leads us to the question, how many valence electrons does magnesium have? How many valence electrons does calcium have? So we said that magnesium's electron configuration, or its noble gas configuration, is neon 3s2. So that means that magnesium has two valence electrons. And then how many valence electrons does calcium have? So we said that calcium's noble gas configuration was argon 4s2, which means that calcium has two valence electrons. So then what predictions can be made about the number of electrons in strontium's valence shell? So we said that strontium's noble gas configuration was krypton 5s2. So that means that strontium also has 2 valence electrons. And remember, magnesium, calcium, and strontium are all in group 2, or 2a. So the number of valence electrons is equal to the group number. However, we're going to use the US system. So for instance, let's look at fluorine, for example. Fluorine is in group 17 or 7a, and it has 7 valence electrons. So we're really looking at that US system or the Roman numeral. So that's a super easy way to determine how many valence electrons an element has. Just look at the group number in Roman numerals, and that will tell you the number of valence electrons. You'll also notice that all of the other elements in group 7a also have 7 valence electrons. So if you were to write out their electron configurations, you would see that their highest energy electrons, they might be in different energy levels, but they should have 7 electrons in that highest energy level. Now, I kind of skipped this last question here. What other element on this chart has similar properties to magnesium, calcium, and strontium? So the other elements in group 2 are beryllium, barium, and radium. And you can consult your periodic table just to make sure I'm correct. But those 3 elements also have 2 valence electrons, and they're also in group 2. And remember that elements that are in the same group or column have the same or similar chemical properties. And then here is the solution slide. So some other properties that we can talk about are, for instance, metallic character. You might remember that previously we discussed metals, metalloids, and nonmetals, but let's talk about them again in a little more detail. So on this chart, you can see metals are highlighted in purple. So the majority of the periodic table consists of metals. And then in the upper right-hand corner, we have nonmetals, which are highlighted green. And in between metals and nonmetals, we have metalloids, which are highlighted yellow. So we actually don't have very many nonmetals in the periodic table, but we can actually still make a lot of different compounds from nonmetals. One other thing to notice is that hydrogen is listed with group 1, but it is not a metal. And remember that group 1 is referred to as the alkali metals. However, hydrogen, even though it has similar properties to the other elements in group 1, it is considered a nonmetal. So let's talk about some properties of metals and nonmetals. So most metals have the following properties. They have high thermal conductivity, which means that they can conduct heat really well. So for instance, a lot of your cookware is probably metal because it can transmit heat really easily. Most metals also have high electrical conductivity. So they can conduct electricity really well. And that's why some wires, for instance, are made of copper. Metals are also ductile and malleable, which means that they can be shaped into wires or sheets. And then they also have metallic luster. And then nonmetals have properties that are opposite those of metals. So they're typically brittle, powdery solids, or they're gases. And typically they're good insulators. So if we look up above, we have a list or a range of elements that are all in group 5A or group 15. And if you pull out your periodic table, you'll notice that nitrogen and phosphorus are nonmetals. Arsenic and antimony are metalloids. And then bismuth is a metal. So in group 5, we actually have a whole range of these different types of elements. However, they do all have similar chemical properties. And you'll notice nitrogen is a gas, and phosphorus is kind of dull. And arsenic and antimony have properties of both metals and nonmetals. And then bismuth is a metal, so it has high thermal conductivity, high electrical conductivity, and it can be shaped into wires or sheets. So again, metalloids are elements that are in between metals and nonmetals, and they form kind of a diagonal line. So we could even draw, oh, I started on the wrong part here, but we can draw a little zigzag line going down that diagonal, and pretty much every element along that line is a metalloid except for aluminum. Aluminum is a metal, as well as polonium. But every other element along that diagonal line is a metalloid. And you might remember I talked about silicon a few lectures ago. The reason Silicon Valley has its name is silicon is used in a lot of computer chips and other devices. And silicon is both an electrical conductor and an insulator, so it has properties of both metals and nonmetals. Also, these metalloids can be used in solar panels, for instance, and there's a lot of research being done on which metals or metalloids are best for solar panels. How can we make solar panels more efficient? So after discussing metals and nonmetals and metalloids, we can now talk about metallic property trends. So remember, we said that nonmetals were kind of in this upper right-hand corner, and the rest of the periodic table was pretty much made up of metals. So we can say that metallic character increases going towards the left of the periodic table. And additionally, we saw that in group 5, we went from nitrogen to phosphorus, which were nonmetals, all the way down to bismuth, which is a metal. So that tells us that metallic character increases going down a column. Now, this would be a good flashcard to make. I will also post some online flashcards so that you can remember some of these trends. Now, another trend we can talk about is atomic size. This has to do more so with the number of electrons and protons that are present in an atom. So for representative elements, and remember that includes the first 2 columns and then the last 6 columns of the periodic table. So I'll kind of color those in here. Atomic size is going to decrease from left to right. Or another way of saying that is atomic size increases towards the left of the periodic table. And we'll talk about why that is in a second. Now, for representative elements that are in the same group, atomic size increases from top to bottom. So as we go down a group, atomic size increases. And again, we'll talk about why that is. So here's a nice diagram showing the different sizes of the elements. So you'll notice hydrogen is really, really small, but also fluorine is the next smallest element. And then cesium is really, really big. So again, we said that atomic size increases going towards the left, and then it also increases going down. All right, so let's talk about why. So let's compare lithium to fluorine. So lithium is on the left-hand side of the periodic table, and then fluorine is in the same row or period, but it's on the opposite side. So lithium has 3 protons and 3 electrons. Fluorine has 9 protons and 9 electrons. And remember, these numbers come from the atomic number of the element. So lithium's atomic number is 3, and fluorine's atomic number is 9. Okay, so let's draw a little picture of lithium. So this is the nucleus. And remember, we have 3 electrons. And let's draw our orbital diagram here. So we have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. So we can actually draw those energy levels, and then I'll use, let's see, red to represent the electrons. Okay, so we've got 3 electrons and they're floating around the nucleus, which has 3 protons. Now let's look at fluorine. So here's fluorine's nucleus, and then let's draw the atomic orbitals. So we have 9 electrons, so 2 will be in the 1s orbital. And I'm just drawing half arrows because they're quicker. And then we have 2 more electrons in the 2s orbital. All right, so that takes care of 4 electrons, which means we have 5 left. So we're going to place 1, 2, 3 in the 2p orbitals. And remember, electrons like to be by themselves before they pair up. All right, so now we have 2 electrons left. So now they have to start pairing up. Okay, so we have 2 energy levels again, energy level 1 and energy level 2. And we've got 2 electrons in energy level 1, and then we have 7 electrons in energy level 2. So 1, 2, 3, 4, 5, 6, 7. I did not evenly space those, that's okay. So remember that You can determine the number of valence electrons by the group number. So for lithium, we have one valence electron because we have one electron in the highest energy level. And lithium is in group 1, or 1A. And then fluorine has 7 valence electrons. And it is in group 17, or 7A. Oops. Writing my Roman numerals incorrectly. There we go. So if we look at lithium versus fluorine, the way I drew it, fluorine looks bigger. But from the previous chart, we know that fluorine, oops, sorry, jumped ahead. Fluorine is actually smaller than lithium. Why would fluorine be smaller than lithium? Well, it has to do with the ratio of protons, or the positive charge. So lithium, again, only has 3 protons, or a 3+ charge in the center nucleus. Whereas fluorine has a 9+ charge in the center. So with fluorine, we have a much larger positive charge in the center, and that's going to attract electrons closer to the nucleus, which makes the atom smaller. So we can write here more protons equals more attraction to electrons. So that's going to equal a smaller atom. Whereas for lithium, we have less protons, which means less attraction to electrons, and that equals a larger atom. So you could also just memorize the trend, but sometimes it's nice to see why a trend exists. Now let's compare lithium to sodium, which is right below it on the periodic table. So we'll look at the trend going down a column. Okay, so let's draw the nucleus. And sodium has 11 protons and 11 electrons. And if we draw out its electron or orbital diagram, actually this is quite long. So this is 1s, 2s, 2p, 3s. Okay, so let's fill in the electrons. So we'll put 2 in the 1s orbital, 2 in the 2s, and then 1, 2, 3, 4, 5, 6 in the 2p orbitals. So we have 10 electrons there, and we have 1 left, which will go in the 3s orbital. So this tells us we have 3 energy levels in a sodium atom. And let's draw those electrons. So we have 2 in the first energy level, and then we have 8 in the second energy level. So 6 plus 2, 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1 electron in that outer energy level. So that means that we have 1 valence electron for sodium. But that makes sense, right? Sodium is in group 1, or 1A, similar to lithium. So they both have 1 valence electron. Now, their valence electrons are in different energy levels, but they should still have similar properties because they have the same number of valence electrons. So sodium, if we remember our atomic trends, should be bigger than lithium. And we can see that it's bigger because it has more electrons and more energy levels. So as we go down a group, we're adding more and more energy levels. So for instance, if we jump down to potassium, potassium is in period 4, and its valence electrons are in energy level 4. So potassium will be bigger than sodium. So as we go down a group, we are increasing electron energy levels. Oh, my pen is freaking out. And so that equals larger atoms. Okay. So hopefully that helps a little bit with understanding the atomic sizes of elements. So remember, as we're going towards the right of the periodic table, we're adding more protons, and with more protons, we get more attraction to the surrounding electrons. So that's going to decrease the atomic size. But then if we go down a group, we're adding on more energy levels for the electrons, and so that's going to increase the size of the atoms. Now, the last trend we're going to cover is something called first ionization energy. And the first ionization energy is the energy required to remove one electron from a neutral gaseous atom of an element. So if we were able to turn all of these atoms into gases and remove an electron, the energy that's needed to remove that electron is what we call the first ionization energy. So for representative elements, so again, the first 2 columns and then the last 6 columns, in the same period, the general trend is an increase from left to right across the period. And for representative elements in the same group, the general trend is a decrease from top to bottom down the group. Now, we're ignoring the transition elements here because they don't tend to follow these trends, so don't worry about the transition elements. So off to the right, you can see we have the representative elements and their ionization energies. And you'll notice that going from left to right, the energy is increasing. Or it's generally increasing. There's a couple of discrepancies in there. And then as we go down a column, the energy is decreasing. So we're increasing going left to right and decreasing going down a column. So let's talk a little bit more about what this ionization energy is. So for example, if we look at lithium again, we said that lithium has 2 energy levels, and 2 of its electrons are in the first energy level, and 1 of its electrons is in that second energy level. Now, what if lithium loses an electron? What ends up happening is lithium is going to lose that outer valence electron, and it will end up with just 2 electrons in energy level 1. So originally, lithium had 3 protons and 3 electrons. But once it loses an electron, it still has 3 protons, but only 2 electrons. So now if we add that together, so we have 3 positive charges and 2 negative charges. So if the positive and negative charges cancel, we'll still have one positive charge left over. So we're actually going to add a little positive charge to our product lithium there. And that is called an ion. So previously we said that different atoms of the same element can have different numbers of neutrons. We said that the number of protons will always stay the same for an element. And now we can see that we can have different numbers of electrons as well. And this is going to result in what's called an ion. Now, metals like lithium typically lose electrons, and then nonmetals can gain electrons. So nonmetals gain electrons. So you can also have negatively charged ions, but we'll talk about that later on. For now, just focus on this first ionization energy. And if we go back, again, we saw that the ionization energy increases going left to right. And part of that has to do with the attraction of valence electrons to the nucleus. So actually, let's go back to this diagram. Remember that fluorine was much smaller than lithium because it had more protons, and the electrons were more attracted to the nucleus. So it's going to be a lot harder to remove an electron from fluorine because all those electrons are really attracted to the nucleus. So we would have to put in way more energy into fluorine in order to extract an electron. But in lithium, which is on the left side of the periodic table, the electrons are not as attracted to the nucleus, so it's pretty easy to take an electron away. Now, if we go down a column, we said that the ionization energy decreases. So if we go back to this chart that I drew and compare sodium to lithium, sodium is below lithium and it has a smaller ionization energy. That's because its valence electron is further away from the nucleus compared to lithium's valence electron, which is closer to the nucleus. So if an electron is really far away from the nucleus, it's going to be easier to pull it away because it's further away from that positive charge in the nucleus, so it has a weaker connection to the atom. So we would need less energy to remove an electron from sodium compared to lithium. But remember, we need a lot more energy to pull an electron away from fluorine compared to lithium. Okay. So I think we'll stop lecture there today. This is the end of chapter 3. And in the next chapter, we'll start talking more about other properties of elements. We'll talk about some chemical reactions that can occur with the elements. So we'll start getting into even more awesome stuff. All right, so I'll see you then.